Welcome back. In today's lecture, I am going to talk about intuitive idea of stability. You can see that I have written intuitive idea. So in today's lecture, I am not going to talk about the mathematical way to represent the stability. Just I will give you the idea how basically concept of stability comes into picture, and if you are going to talk about any design problem, any analysis problem, then this concept is pretty much required. And due to that reason, today's lecture is very important. If you understand the intuition, then equally you are able to translate that intuition into some mathematical framework. And due to that reason, first I decided that I will start from the intuition only, and first part of this intuitive idea is based on some kind of graphical method. So I am going to plot some graph between something and try to understand that what is idea of stability. Second way, I am going to tell you about the geometrical picture. So those who has attended the course of mean sliding mode control, they have already idea of that kind of things. So I am going to repeat in sake of completeness. And after that, third part is based on the solution. So these are standard three different way. Basically, we are going to characterize the stability of any dynamical system. So if you see the previous class, what we found that if I have some system, so you can take any simple system. So I am going to take some first order system. So if you remember the previous class, then I have taken very simple system. So I have certain kind of object, and object has some temperature T, and surrounding temperature of this is Tm. And after that, what basically we have done, we try to understand that how basically temperature of this particular object, I am assuming that temperature of this particular object T is greater than the surrounding temperature, and using Newton's law of cooling, if you remember, then I have written this kind of mathematical equation, and after that I have some kind of constant and T minus Tm. Okay, so this is our mathematical equation, and after that what basically we are telling that T belongs to some kind of real number, and this is the temperature of the surrounding, and K we are assuming that is greater than 0. And what we found that I am going to plot the temperature on this real line, and if T equal to Tm at this particular point, suppose this is Tm, then rate of change dt by dt equal to 0. So once rate of change is C, then I can tell that at this particular point, and this particular point in whole state space. So in this whole state space, I have only this single point which has certain kind of property that if you are going to start from this point, since rate of change is 0, due to that reason you are going to remain here if there is no disturbance, no any kind of external perturbation. And we have defined this point as a equilibrium point. If you check the another literature, then people are telling fixed point or equilibrium point. In this lecture, I am going to assume everything has same meaning. Okay, it might possible in some another literature people are differentiating between equilibrium point, origin, fixed point, equilibrium point. But in this particular lecture, a particular course, I am assuming that notion of equilibrium point, fixed point, or origin, everything is exactly the same. Now let us come to the another question. So what we found that using the notion of equilibrium point, at least I understood that I have certain kind of reference point in a state space, such that if I start from that point, I am going to stay there. Okay, now next question comes into picture, that suppose if I do not start exactly from this point, then what is my behavior? So suppose if I start in the vicinity of this equilibrium point, so I know the behavior of this point. that if I am going to start, I am going to stay here. But now I am going to show the behavior, or I am going to understand the behavior if I am going to start nearby of this equilibrium point. And whatever behavior that comes into picture, that is connected to this notion that is called notion of stability. Anyone has confusion on this? Are you able to understand the difference between equilibrium point and stability about the equilibrium point? Anyone? Taslima?
Yes, sir.
Any other guy? Okay, so I at least I understood that now you have do not have any confusion that equilibrium means I am going to talk about some point and we are going to see the exactly behavior about that point. But whenever we are talking about stability, then we are going to talk the behavior nearby of that point, because most of time during several interview, whenever I am asking a student that what is difference between stability and equilibrium point, so they are giving same answer, but that is not the same. Due to that reason, I am going to first clarify that are you able to understand the difference between these two. Okay, now let us try to see the outcome. So basically in some subsequent lectures we are going to handle these questions. Okay, so in one lecture it is not possible to handle all questions, but intuitively you are able to understand lot of things in today's lecture. So basically we are going to talk how to define stability of dynamical system. Okay, so different notions we are going to introduce, and after that how is the stability of dynamical system is determined. So first we are going to see the definition, and after that we are going to apply that definition to dynamical system, and after that we are going to talk about the stability. One more important point I am going to highlight here using third point, that whenever we are talking about some linear system, okay, so what is property of linear system, that either we are telling that equilibrium point is stable or whole system is stable, both have exactly same meaning. But in case of nonlinear system, that is not the case. Why? Because I have more than one isolated equilibrium point. If you remember the previous class, you might have seen that in case of the pendulum system, I have infinite many equilibrium point, and out of that we have characterized equilibrium point in two sets. One equilibrium point is here, one equilibrium point is here. And what we found, that behavior of this equilibrium point and this equilibrium point is not the same. If you apply some small perturbation here, then what happens, again my behavior is like this, but here if you apply some small perturbation, then I cannot able to maintain this position. And due to the several isolated equilibrium point, I cannot talk about stability of whole dynamical system. I have to talk stability about some kind of reference point, and that reference point is equilibrium point, because we know at least that if you are going to start from that point, you are going to stay there, and due to that reason we are selected that point as a reference point. But if you see the linear dynamical system, which is represented by like this, I am going to just talk about autonomous system, or you are going to take like this, at into xt, here t is also involved. And in this particular system, if this matrix A has some specific property, then it is possible to show that x equal to 0 is the unique equilibrium point. Okay, so and if I have more than one equilibrium point, then all equilibrium point is connected. So due to that reason, what we are assuming that without loss of any generality, that I have unique equilibrium point. So either you can take about stability of equilibrium point or stability of whole system, notion remains the same. Okay, so either you can write that linear system is stable or equilibrium point is stable, both are exactly same, but that is not the case of nonlinear system. So now whenever we are going to talk about stability, first we are going to tell that we are going to talk stability about which point. So suppose in case of pendulum system, I am going to tell that okay, I am going to talk stability about this lower point, I am going to talk stability about the upper point, and behavior is totally different. And due to that reason, if you are going to write that some dynamical system is stable, then that is wrong statement. So please be careful whenever you are going to write papers or anything. Okay. So now this question we are going to understand that why do we use the term local stability? Local because here you can see that you know that behavior of this equilibrium point and behavior of this equilibrium point is totally opposite. Okay, so I can tell that okay, this particular equilibrium point, lowermost equilibrium point, has some kind of behavior. I will define stability, what is meaning of stability in the later part of this lecture, such that I can tell or give guarantee that if I am going to start in the neighborhood of this equilibrium point, or our initial condition is neighborhood of this equilibrium point, then I have some kind of converging behavior, converging kind of behavior. But here I have some kind of diverging kind of behavior. And due to that reason, whenever we are talking about the stability of nonlinear system, then we are going to put this word particular word local stability most of time. But I am not denying that some nonlinear system also has unique point, and I can tell the stability of whole system. That is also possible. So that is the best case. After that, you can see that another, this fourth point is very important. And whatever oscillator or what is oscillation related phenomena we are using, you might have seen that in electrical system what is role of oscillator has various role. In medical field also we need we need phenomena of oscillation. And due to that reason, now how to construct oscillator, and it is possible to show that it is not possible to construct or at least understand the oscillator if you are not going to understand the theory of nonlinear control system. So fourth question is related to that: can a linear dynamical system generate a stable or sustained oscillation? Because most of time, suppose you have to produce some kind of sinusoidal wave, then you need some kind of sustained oscillation. And it is possible to show that using linear dynamical system, it is very difficult or impossible to create the sustained oscillation. Obviously, if I will take everything is ideal, then one can create using linear dynamical system, but that is not the case. Now here, fifth question: suppose that a dynamical system has one unstable fixed point. Is it possible for a system to be stable in some sense? So it might possible that some system is locally unstable but globally stable. So that kind of phenomena is also very much obvious in nature. Okay, so due to that reason, we have to understand different notion of stability for this particular purpose, and we are going to understand the notion of limit cycle in the subsequent lectures. And obviously one of the most beautiful outcome after that, that is Lyapunov stability or function, and we are going to connect this with this particular notion of stability. So this is somehow the the outcome of next 4 or 5 lectures. Okay, and everything is connected with the stability. And due to that reason, if you are going to not understand the stability precisely, then you are not able to appreciate these kind of phenomena. So let us start the today's lecture. So in today's lecture, I am going to start with some dynamical system. So I am going to take this as a black box system. So I do not know what is inside this. I know that this system initially actually operate on some fixed point. Operating on fixed point means somehow we are interpreting that all initial condition has some specific value. Either you can take 0 also, that doesn't matter. Okay, so or you can interpret from this particular equation, then things become more clear. Suppose I have some system x dot equal to fx, and what is the name of this class of system? Silpi, could you please tell me what is the name of this class of system?
Autonomous system.
This is called autonomous system. Okay, so I have autonomous system. So now Ankit, could you please tell me that what is input of the autonomous system? Suppose now I am going to represent this system in form of input and output. Then what is my input and what is my output? Ankit, are you here?
Yes, sir. Yes, sir. Yes, sir.
Okay. So could you please tell me that output I am going to tell you, output is xt. Okay.
Yes,
Then what
sir.
is input?
FX.
Try to recall the notion of a state. What notion of a state is telling? Because
Actually, I don't remember, sir.
what?
I don't remember, sir.
Okay. So please revise carefully. So anyone, could you please, Vinay, could you please tell me that what is input here?
So in this case, the initial state will be the
Yeah.
input.
Initial condition, initial whatever. So whenever we are writing differential equation, so that has no meaning. Okay, due to that reason, whenever you are writing differential equation, at the same time you have to specify the initial condition also. So suppose if I know the initial condition and if I know the differential equation, since whenever we are writing this kind of equation, we are assuming that this part is known to me. Okay, so due to that reason, this is not our input. So input is just x0. So x0 is my input and xt is our output. Suppose if you are writing system like this, x dot t fxu. So baby Dana, what is name of this class of system? Baby Dana, are you here?
Yes, sir.
What is name of this class of system x dot equal to fxu?
Autonomous, sir.
Autonomous. This is autonomous system, but here I have introduced some another thing u. This is called force system. Okay. Okay, please revise everything again. And xt is here output, and here again I have two input. One is the initial condition x0 and another is control u. Okay, so in this case, if I know the initial condition and u, and if I know this differential equation, then I can uniquely able to predict the future. That is the interpretation. Okay, up to here anyone has confusion? Okay, now let us, what I am going to do, I am going to take some kind of force system only. So you can see that here I have given ut and somehow initial condition is hidden. So here I have some kind of initial condition. So suppose if system is operating about some specific point, and I am assuming that I am not going to apply any force at that moment. So system is either at rest or operating about the equilibrium point. Okay, so what happens after that? What I am going to do, I am going to apply some force ut, and after that I am going to remove that force. So what happens that my question, next question is that what happens if we suddenly displace the system away from the fixed point and then just quickly release the displacement force. So I am interpreting this force as a displacement force. So what basically we are telling that, suppose my system is in rest and after that I have suddenly applied some kind of force, and what that force is going to do, that my initial condition xt0 is 0 initially. Now due to influence of this force ut, I have certain kind of initial condition now, that xt1, suppose I have applied force, whatever force I have applied at t1, so that is x0. Okay, so initially system is operating at operating on the zero initial condition. Now I have finite initial condition. So now we are going to characterize the behavior of the system. So now it means that whatever system I have, that is governed by this particular initial condition, and we are going to note the behavior xt, or you can write output yt. Okay, so basically if you see, then what happens that whatever fixed point, so I have already told you in the previous time that when T equal to Tm and I have some system which has temperature T and surrounding temperature is Tm. So if you are here, and what is behavior of equilibrium point, that if you start from here, you are going to stay here. So if you are going to perturb from here, then this actually generates some kind of resistance. Okay, so mathematics people or control people has given certain name to that resistance. So somehow you are in some type of rest, you can tell. And if you are going to change that, then some resistance is actually comes into picture, and that change, whatever change or behavior of that change, which comes in this topic, that is topic of stability. If you have done course on linear control system, you might have seen that what people are telling, that if I apply bounded input, then I will get bounded output, then system is stable. But here we are going to generalize that particular idea for general class of system. Okay, so what basically we are telling, that okay, I have applied some force and after that I remove force. It means that now my system is autonomous. So I have certain initial condition, and after that we are going to see the behavior. Okay. So now what happens, that we have two different kind of behavior. It might possible, since I know that in this whole state space I have just this point t equal to tm, that has behavior that if you are going to start here, you are going to stay here. So it might possible that after a small perturbation and after long time again I can come back to this temperature t equal to tm. Okay, so I have this kind of behavior, and it might possible that I cannot able to return here, I will go beyond this. Okay, so I have two different behavior, and in case of pendulum system you have already noted these two behavior, that if I start in the neighborhood of this equilibrium point, then again I can return back, but if I start here, then I can never return back. So if I am able to again return back, then system is called stable. Or basically I have already told you that in dynamical system I have more than one equilibrium point, so I cannot able to talk about stability of whole system. I have to talk stability about the equilibrium point, and due to that reason we are telling that whatever this fixed point or equilibrium point that has behavior, that is called a stable behavior. But whatever this point, since if I will give a small perturbation, then I cannot able to regain again this position, and due to that reason this behavior is called unstable behavior. So first people has characterized behavior like this, that stable behavior and non or unstable behavior. So believe on me that if you take a linear system, then I have just two behavior. Either system is stable, whole system I am talking about, stable, unstable, and sometimes people are telling marginally stable. Okay, so just I have three different kind of behavior, but nonlinear system has several different behavior, and in subsequent lecture we are going to see that apart from stable or unstable behavior, we have different kind of other behavior also. Okay, so in today's lecture I am going to focus myself just on first order system. In next lecture I am going to talk about second order linear as well as nonlinear system and their behavior. So what happens, a dynamical system can be stable in some sense on a large scale even though fixed point is locally unstable. So this kind of behavior later people has observed. Okay, and what they found, that this kind of behavior is only shown in case of nonlinear system. So what they found, that suppose I have this equilibrium point. So system is unstable means if you are going to start in nearby of this, then trajectory start diverging from here. And it is possible to show in case of limit cycle, I have some connected equilibrium point here, and in this particular connected equilibrium point, what happens, if you start from here, then enlarge, then you are going to converge, but if you start nearby of this, then you are going to diverge, and finally you are going to converge in this particular orbit, and this is called limit cycle. So somehow this is also characterizing the behavior of stability only. So I can not only tell that if I start in nearby and what is my behavior, so that is another prospect and this is another prospect. So we are going to talk both prospect in this particular course. Anyone has confusion on this? Anyone? So this first prospect is basically generated from the linear system, and second prospect is basically inherent property or some kind of beautiful property of the nonlinear system. Okay, now what I am going to do, I have told you that I am going to visualize stability in different geometrical way, different graphical way. Okay, so let us try to understand the graphical demonstration of the stability. Okay, so you might have seen, suppose that if you have some kind of wheel like this, okay, vertically upward, and if you are going to throw some ball here, then what do you think? What is the behavior? Anyone? I have some kind of curve like this, and here I have here I have wall like this, and I have some kind of ball here. Then what do you think? What is our behavior? Suppose we are in the influence of gravitational force. Anyone?
It will have oscillation, sir.
Yeah, it is oscillation, and what happens? After some time oscillation is going to decrease, and finally we are going to come here. Okay, or in another way, what you can do, suppose initially I have ball here, and if I displace this ball by using some small force, then what happens? That if I am going to displace from here to here, and since I have some kind of gravitational field, and due to that reason, what happens? That after some time I am going to return here. So I have this kind of behavior. Second behavior I can expect like this. Suppose I have this kind of hill now, and if I have initially here ball, so I am assuming that here if you are going to put ball here, and if you are not going to apply any force, then ball remains here. Okay, but if you apply some small force, you can see that ball is not going to return back from here. So by mechanical analogy or some kind of electrical analogy, it is possible to show that how to construct this kind of surfaces, and after that characterize the stability graphically. Okay, so we are going to construct this using the help of mechanics. Okay, so basically notion of stability is arises from the mechanics. Okay, so what people has observed, that if I have some kind of conservative field, meaning of conservative field is like this. Suppose if you move from here, from like this path or this path, any other path, if these fixed 2 points A and B are the same, then work done or whatever potential that remains the same. Okay, that is not depending on the path from A to B, that is independent of the path. And based on that phenomena, I am going to construct some kind of potential function, and after that we are going to see the behavior of potential function with respect to the state. Okay, so I hope that you all are already well aware that the potential is equal to work done when an object is moved between two positions in the presence of force, conservative force I am telling. But suppose if you have non-conservative force, then I cannot claim like this. Okay, and why we are going to use this kind of analogy? You can see that whenever I am writing this kind of autonomous system, then most of time we are talking about some kind of behavior that is autonomous, not influence of any external thing. So due to that reason, I am going to use that kind of analogy. So this kind of analogy is only applicable when this particular function is not explicitly depending on the time. So I am talking about autonomous system. It is possible to show that force, this is fx, and this is potential function is related to this. I hope that during your 10 plus 2 you are able to see this kind of relationship, force equal to dou u by dou x. Now what we are going to do, that we are going to use the concept of potential function, and using that potential function I am going to do some kind of modeling in terms of flow. We are telling that whatever potential function, that is nothing but some kind of flow, and flow we are going to construct with respect to some surface that is called potential surface, and I am going to plot these two, same like whatever example I have given just now, that I have this kind of shape or this kind of shape. since I am just dealing with the first order system, and due to that reason I am going to construct curve in two-dimensional plane. Okay, now what I am going to do, that in order to construct this potential function ux, I am going to consider this kind of dynamical system, that is dxt by dt equal to fx, and I am going to take the first order system. Due to that reason x belongs to R. So the key point of construction of a dynamical potential ux is to recognize that right hand side of this. So what basically we are going to do now, I am going to interpret this fx as a some kind of forcing function. Why I am interpreting that as a forcing function? Because you can see that xt is some variable, and rate of change comes into picture due to this particular variable fx only. Okay, because dx by dt equal to fx, I have taken this kind of model. So what basically we are interpreting, we are interpreting that this particular function fx is responsible for the rate of change, and that is nothing but that is exactly equal to this particular force fx. So based on that methodology, people has constructed this function ux. So we'll try to see in the next part of this lecture. You can see here that dx by dt equal to fx, and here this force fx and this force which is responsible for the rate of change, that is exactly equal. Okay, so due to that reason I can write like this. So from here these two relation I can able to construct this ux, that is integral, finite integral from 0 to xt fx into dx. And now you can see that in this way I can see the ux, but you have to see that what is behavior of this ball about this particular curve, and due to that reason you have to calculate the rate of change. So if you calculate the rate of change dux by dt, so that is here you can see that u is function of xt and x is function of t. So t is the implicit function of u, and due to that reason I have dou u by dou xt by dxt, and after that dxt by dt. So you can see that this particular variable from here, that is minus fx, and after that dx by dt is also already fx. So I can write like this also. So it means that if I have this magnitude is positive, so from this analogy I can tell that potential is actually decreasing with respect to time. Okay, now what I am going to, this is very generalized case, but now we are going to take a special case, and in a special case I am going to take the linear system. So what I am going to do now, I am going to take this system dx by dt and kxt, and for this system I am going to construct some kind of potential function. Okay, so again in order to construct the potential function, what is our strategy? We are going to equate this particular variable with dux by dx, and after that I am going to solve for ux. So if you solve for ux, you can see that this kind of things comes into picture. Anyone has confusion on this? Anyone? Because in previous relation we have seen that this is nothing, ux is nothing but integral of fx. Okay, so in place of fx you can just substitute the right hand side of differential equation. So here I have right side is minus kx, so I am going to substitute here. Okay, and after substituting, if you calculate this finite integral, then you can able to see this. Okay, now what you can do, you can draw the curve between ux and x. Okay, and you can see that I have some kind of parabolic curve in two-dimensional plane. And now what you can do, you can put one ball and give some displacement. Okay, so ball analogy you can tell. So in this way I can tell that dynamical potential is related to stability. So if I have this kind of situation, then I can tell that okay, my system is unstable by plotting. If I have this kind of system, then I can tell that this system is stable. So for linear system, I have system is either stable or unstable. Anyone has confusion on this, then please let me know. Anyone? Okay. So now you can see that I have written same thing. If we change the sign of k from positive to negative, so if k is positive here, k is greater than 0, then I have this kind of curve. So direction of this parabola is upward. But if you reverse k by k less than 0, so here negative sign comes into picture and I have this kind of shape. And if ball is here, then you can see that my behavior is unstable, because if you displace flight from the equilibrium point. Why this is equilibrium point? Because if you put ball here, and if there is no external force, then here this is at this point, and from here also you can see that at this particular point my potential, whatever potential function, that equal to 0. So if potential equal to 0, then what happens? I am going to stay here. But if you displace here, then what happens? That if system is unstable, then potential is going to rise, and due to that reason I have either in negative side and positive side, that doesn't matter for me. Okay, so anyone has confusion how to construct the potential function for first order case? Okay, let us try to see the some nonlinear system. So I have taken again this nonlinear system, and since I am going to talk about intuitive idea of the stability, so due to that reason I have taken all examples from some practical system, and you can see that all linear system can be characterized. First order linear system is represented like this, and here I have taken some biological system, and actually that system is called excitable system. Excitable system means you might have learned, those who has some idea of biology, that what happens that whenever some information or some excitation come to the neurons, then some firing comes into picture, and in using that firing, basically information is transferred from one point to another point. If firing magnitude is small, then what happens, or excitation magnitude is small, then firing is not going to happen, and it is possible to show that will follow this particular nonlinear dynamical equation. So fx here in this particular example, fx is some linear part, and after that I have some cubic nonlinearity, you can take. And again, if you are trying to find the potential function, so again you can take 0 to x, and after that you can take the definite integral, and you are able to see this. Now here you can see that this is the plot of this nonlinearity fx, and here, but in this place, if you plot between ux versus x as a x-axis, and this on the u-axis, so this is nothing but ux. So you can see here that I have two places where I have this kind of situation. Okay, and here if you are going to put ball here, so either they will fall in this direction or this direction. Okay, but if you are going to put ball here, then you can see that again I have a stable behavior. If you put ball here, again I have some kind of stable behavior, and this kind of stability is called the biostability, and nonlinear system only exhibit this kind of stability. Linear system never exhibit this kind of stability. And again, the fixed point at 0 is unstable at the hilltop, means we are telling that this point is unstable, more generally called repeller. So this point is called repeller. So in next lecture, when I am going to talk about phase plane analysis, then this kind of terminology I am going to use. Okay, but these point -1 and +1, that is called valley point, and these are the attractors. Attractors means if you displace sudden a small displacement, if you are going to provide, then this point is going to lose their position, but after very large time they are going to return back, and due to that reason we are characterizing this as a attractor. So this is one of the way to see the stability in graphical fashion. What you can do, you can use the idea of potential function, construct the graph by taking definite integral, and after that you can see the plot. So this is one of the graphical way to see the notion of stability for first order system. It is possible to show that this notion is further extended by Lyapunov for the higher order system. So all Lyapunov theory is just extension of this particular notion. So we are going to talk that in the next part of this course, but in today's lecture we are going to see the different way to recognize the idea of stability. Now I am going to tell you the geometrical way to represent stability of first order system. In the previous class, I have already taken this example. This is nothing but some kind of underwater vehicle, and I have already told you that I have one thruster, and after that here I have to control the velocity. Okay, so and for that I have this kind of dynamical equation. So since I am going to control the velocity of this, I am going to apply the Newton's law, and I am assuming that mass of this underwater vehicle is unity. So I can going to use F equal to mass into acceleration. So acceleration is nothing but dv by dt, and due to that reason and mass is unity, so left hand side comes into picture. And after that I have told you that u cap is the force due to thruster, and this is nothing but some kind of opposing force. Okay, so that is going to oppose the motion, and here due to flow I have some kind of uncertainty, and I have two different problem. I have told you that in presence of flow I have to stop this underwater vehicle, that is called stabilization problem or robust stabilization problem. And tracking problem is that suppose I have to move this underwater vehicle on some sinusoidal with some kind of sinusoidal velocity or some kind of velocity. Okay, so that is called tracking problem, and this is robust tracking because D I have I am assuming that D is not known to me, but D is somehow bounded for all T. So this kind of assumption we have. So this is called robust tracking and stabilization problem. We will talk about this particular control problem in the further part of this course. And now you can see that this system is no longer linear because here I have some kind of non-linear term. So I cannot talk about the quantitative behavior of this system. Okay, so quantitative behavior means if you have linear system, then you are noting rise time, settling time, these kind of things you are noting. After that, in frequency domain, you are seeing that where is open loop transfer function is going to lie if you are going to increase the frequency from minus infinity to plus infinity. But that kind of things I cannot do here, and due to that reason, whenever you have non-linear system, then you have to talk about stability not in quantitative way but qualitative way. And qualitative notion means using some kind of analogy. I am going to talk about the behavior of the system. So exact behavior is not required, approximate behavior is okay. And actually stability, accuracy and speed of response, robustness or cost, these all things are somehow qualitative in nature. I cannot tell exact cost, what exact cost is involved in any nonlinear system, and due to that reason everything we are analyzing in terms of approximate way. Now let us come to the stability. So what I am going to do, I am going to design some kind of control action first. Since my system in the previous page, you have seen that I have this kind of system plus dt, and I know in advance that when some object is moving inside the water, then whatever friction force comes into picture, that is proportional of the square of the velocity. So I am going to put that force here, and I am going to design u, and I am assuming that u is just function of this velocity. So this is called proportional control action, and for time being I am assuming that d equal to 0, and I am going to design now control that is based on the present information of the velocity. I am going to solve the stabilization problem. Stabilization problem means I am going to stop this underwater vehicle, and I am assuming that there is no disturbance. I know the exactly everything. At that time, I am going to analyze this system v dot equal to minus k into v. Okay, so from stability, I am able to design this gain. Okay, that is our main task. So if you are going to analyze this system, then you are also telling that what is sign of kp. I have already written kp greater than 0. Let us try to give the argument that why I have selected this kp equal to 0, kp greater than equal to 0. So I have taken this, and I have already told you that whenever we are talking about the engineering system represented by differential equation, then I have to provide the initial condition, and due to that reason I have provided initial condition vt0 equal to v0. And this system, after that, after substituting control, you can see that this is nothing but I have some kind of autonomous system, and this is first order autonomous system because vt belongs to r. So we are telling that here I have, this is the real line, and Vt somehow belongs either in this positive side or negative side. And due to that reason, you can see here that whenever I am going to talk about stability, I have drawn geometrical picture like this using some kind of real line, and after that I am going to take all or consider all possible case. So I have differential equation like this, and after that first I am going to consider that V0. So this is Vt. So V0 I am going to consider that is positive. Okay. So and suppose Kp is greater than 0. So could you please tell me that what is V dot T? Ankit? Ankit, are you here?
Yes,
So
sir.
so what I am telling that
Yes,
Kp is
yes, sir.
positive and initial time t equal to 0, this is positive. So what do you think? What is V dot? Positive or negative? At time some time t equal to t0 I am telling. Kp is positive and Vt is positive. So what is V dot?
Negative.
Negative, obviously negative. It means
Yes,
that
sir.
if you are in this side, then rate of change is negative. So I know that in real axis we are taking positive direction like this in this side, and wherever something is negative, it means that I am going to do reverse. Okay, and from Newton's law it is clear that some quantity is positive but rate of change is negative, then that quantity is going to decrease, and due to that reason I have this kind of behavior. Now let us check on this side. I have already discussed about this in previous class also, that if Vt is negative, then what happens? Negative negative that become positive. So now I have V dot is positive, and what is positive direction? This is our positive direction and this is our negative direction. So I have to move in direction of the rate of change, and due to that reason I am going to move like this. But if you are going to start here, then what happens that V equal to 0 at this point, so V dot also equal to 0. So from Newton's first law, I can give guarantee that I am not going to move. So due to that reason, this is equilibrium point. So what happens that if you start anywhere, if I am going to design control like this, and if I start anywhere in this state space, you can see that what happens that I have what kind of behavior? Behavior is stable or unstable? Anyone? Sunidhi, could you please tell me that behavior is stable or unstable?
So stable.
Stable, because we are converging. Okay, now what you can do, you can just change the sign Kp negative. Then what happens? You are able to see that at that time my behavior is totally opposite like this. If you start anywhere, even if that is very very close to the equilibrium point, you are going to divert. So using Newton's law also, you are able to see the stability of the first order dynamical system. Okay, now you can replace this system like this, V mod V. Okay, what you can do, you can take same system and assume that you are going to switch off this force. So in this particular example, I am going to take, suppose what I am going to do, I am assuming that I have no disturbance, and at some moment I have switch off this U bar. Again, you try to see that behavior by same analogy. So now my system is V dot equal to minus V mod V. So again I can plot this, and you can see here if I have no disturbance, then again I have similar kind of behavior. Anywhere you can start, you are going to converge to the 0. It means that I am going to remains after some time. Initially I have some kind of rate of change, okay, because I have some kind of initial velocity, but after large time what happens, due to opposition force of the water, finally my velocity equal to 0. Anyone has confusion on this? Okay, so in similar fashion you are able to understand the stability of linear system and nonlinear system. So using Newton's law, you are also able to give the idea of equilibrium point. I have already discussed about this. And what happens, that idea of asymptotic convergence now comes into picture. Why I am telling asymptotic? Try to understand this point. Since my system is V dot equal to Kp into V, so if you start in the vicinity of this, suppose if you start very very large, initially you can assume that you are here. So at that time you can see that if V is here and Kp is fixed, then your rate of decrement is very very fast. Why that is very very fast? Because if V is very very high, then your rate of change is high, and due to that reason, you with large velocity, your rate of change of velocity is very high. So due to large rate, you are going to converge towards the equilibrium point. But what happens as you move closer, then this value Vt is going to decrease, because now we are at this point. You can see that V0 is here, that is 10. So now here this become 2. So multiplication of these two become further small. So I may start moving with a small velocity. Suppose if you are here, again my rate of change is very small. So if you are at very nearby of equilibrium point, it is possible to show that your velocity is almost, or rate of change is almost zero. So it takes infinite time to converge to equilibrium point, and it means that I can never able to catch this equilibrium point. I have some kind of asymptote about this origin or equilibrium point, and due to that reason this kind of convergence is called asymptotic convergence. Anyone has confusion on this? Have you able to understand the motivation of this name, asymptotic convergence? And this kind of stability is also called asymptotic stability. So from Newton's law, you are able to understand the equilibrium point, you are able to understand what is meaning of asymptotic convergence or asymptotic stability both. Now suppose if disturbance is there, then try to see the behavior. So if disturbance is there, then you cannot tell that if v equal to 0, I am going to remain there. Why? Because if v equal to 0, at that moment this system is governed by this disturbance force. Okay, so what happens after some time, this particular value, suppose if you are very far from the equilibrium point, I want to see the behavior about equilibrium point in order to characterize the stability, because now I understood that how to characterize the stability. And suppose if you are far from the equilibrium point, then what happens that initially your Kp multiplied by V part is going to dominate over this part D, and suppose D is positive for time being. If that is negative, then that is very beneficial for us, they are going to support our motion. But I cannot tell the best case, I have to analyze the worst case. So I am going to tell those kind of case where D might be positive or negative both. So this part is able to responsible for the decrement of velocity of or convergence. What happens after some time, value of this is going to dominate over this, and it is possible to show that when these two quantity, when Kp equal to V equal to D, at that time my rate of change equal to 0. So once rate of change equal to 0, then what happens, these two quantity is exactly equal. So I have to stop here, but disturbance is still persisting, and this value is going to decrease. Due to that reason, I can move in this direction. But if you move in this direction, then what happens, disturbance, magnitude of disturbance is now higher. So what happens, they will now pull you back in this direction, but you know the behavior in this direction. So what happens that I cannot move beyond this. So once you enter inside this, then you are not going to leave this region, and this is the notion of stability. So notion of stability is telling that I am not claiming that I am going to converge to the equilibrium point, but I am going to remain in the sufficient vicinity of the equilibrium point. And this is called uniformly ultimately bonded. What means meaning of uniformly ultimately bonded? It means that if you start anywhere in this region, you are not going to diverge. You are going to remain inside this region forever. Okay, so now you can interpret I have some kind of invariant set. Invariant set means if you are going to start from this set, you are going to stay inside this set. So I have some kind of invariant set instead of some point. And if you start from this set, you are going to stay inside that set only. And that kind of notion is called uniformly ultimately bonded. And this kind of stability generally we not desire in case of the engineering system. What is our understanding? Suppose that if I launch some kind of geostationary satellite, so what we are expecting that if due to some disturbance, if this geostationary satellite is disturbed from their orbit, then finally after some time they will converge here again to the original. So but in case of stability, I cannot claim that. Due to that reason, we need some kind of asymptotic stability. Asymptotic stability means after some time I can again return back to the original orbit if I deviated from the our original orbit by some small magnitude. Okay, but if system is just stable, whatever design you have made that is just stable, then I cannot again come back to this original orbit. I am going to stay nearby of this kind of ultimately uniformly bounded. So concept of stability one can also interpret in terms of the geometrical way or way of Newton's. So just you can apply the Newton's law for first order system and you are able to visualize the notion of stability. So anyone has confusion? Are you able to understand the difference between asymptotic stability and stability? Baby Dana, are you able to understand the difference between stability and asymptotic stability?
Yes, sir.
Iram Taslima,
Yes, sir.
Vinay ji?
Yes, sir.
Okay, so these are the notions. So let us try to now summarize it. You can see here that whenever we are talking about stability, then we are somehow talking about boundedness of a state trajectory. It means that if I start nearby of the equilibrium point, my whatever our future trajectory that is going to remain bounded. I cannot deviate much from the equilibrium point. Okay, but I cannot claim that after large time I again come back to the equilibrium point. So this it means that stability whenever we are talking that we are unsafe but I cannot return back. Okay, that is the meaning. Asymptotic stability means I remains bounded, and apart from that, I am going to converge to the equilibrium point after large time. So it means that whenever you are talking about asymptotic stability, so since boundedness is required, so asymptotic stability means stability plus convergence to the equilibrium point. Okay, we are going to see whenever we are going to develop some kind of mathematical notion. Now here you can see that whenever we are talking about asymptotic stability, at that time we are not telling that at what rate I will converge to the equilibrium point. But if you solve this equation, whatever v dot equal to minus k into v, and if you see the solution of this, it is possible to show the solution of this is given by vt0 exponential function k into t. So here you can see that if I have some initial condition vt0, so if my rate of change, if k is positive, k is greater than 0, so exponentially I am going to decrease to the. So it means that if you are here and k is negative, so with exponential rate you are going to converge here, and that is called nothing but exponential stability. So I have boundedness, and after that rate of convergence to the origin is exponential. So I am going to talk about rate of convergence also. In case of asymptotic stability, we are not talking about rate of convergence. So are you able to understand the definition difference between these three notions? Stability means just we are talking that some point is stable for dynamical system. If you start nearby of that equilibrium point, you are going to stay nearby. If that is not the case, then we are telling system is unstable. Asymptotic stability means if you start nearby of equilibrium point, then what happens? Finally, again you are going to converge to the equilibrium point. But what rate you are going to converge, we don't know. And exponential stability means what happens that you are going to remain bounded, and after that you have certain rate of convergence also, and that rate of convergence, if that is exponential, then that is called exponential stability. So most of engineering system require this kind of stability, that is called exponential stability. So we conform the design in such a way such that our closed loop system is exponentially stable. So this is the story. Apart from this, nowadays another kind of stability people has coined. I am just going to summarize within 5 minutes. So another kind of stability, what we observed that in previous case, whenever we are talking about exponential stability, so based on solution or based on intuition we are talking. So you can see that suppose I have this point and I am going to converge at this point. So exponential function is that. So exactly I cannot converge. because this is exponential function. So always I have some kind of asymptote here, and due to that reason also you are able to see that exponential stability also implies asymptotic stability. Asymptotic stability also implies stability, but in this way I cannot tell. Okay, something is stable, then I cannot directly claim that it is also asymptotic stable. But if something is exponentially stable, I can claim that it is also equally asymptotic stable or stable. Okay, now what happens that people start telling that here also, in order to converge exactly at the VT at the equilibrium point, I need infinite time, because this function Vt exactly equal to 0 when t is tending towards infinity. I don't know how large it takes to converge to the equilibrium point. After that, people start noting some kind of phenomena. You can see that in this lecture, whatever phenomena I am going to explain, I am going to explain using some kind of practical example. So here what you can do, you can take one card. Initially, suppose that card has some force Ft, they are moving. What you can do after some time, you remove this force. Then what happens, and suppose I have some kind of friction here, then this cart is going to stop, okay, due to friction. And it is possible to show that mathematical model of this is given like this. This is some kind of static friction or dry friction. You can see kd signum v. That is actually, if meaning of this, if you are moving in this direction, then direction of this friction is opposite. If you are start moving in this, then direction of friction force is like that, means always they are going to oppose the motion. So this is the mathematical model if you are going to remove the external force. So with help of dry friction, we have this kind of model. Okay, if you solve this equation, it is possible to show that within this time this cart is going to stop. Okay, so I can tell that within finite time, if I have no force, then this cart is going to stop. Now what you can do, you can take this system mv dot equal to u. Now suppose this is my control action, and if I design virtual control like this kd signum v, you can see that similar kind of behavior comes into picture because autonomous system remains the same. So by intuition of this particular phenomena, I can able to design control, and after that I can tell that what is behavior of closed loop system. And this kind of behavior is called finite time step, finite time convergence. Finite time convergence means within finite time I can converge to the equilibrium point. But you can see here that whenever we are talking about finite time stability, at that time I have to wait. If initial condition is larger, then I have to wait for large time. So this type of convergence or converging time is function of the initial condition as well as parameter. M and kd is the parameter. Later what happens, these people, Polyakiko people, what they are suggesting, now what you can do, you can put this card inside the water, and suppose inside that water I have some kind of friction force also. Then what happens, one more friction force, that is viscous friction force, and that is a square of the velocity we have just seen now. So either you can write like this or like this, both are same, both notion is same. Here signum v is nothing but when v greater than 0, then that is plus 1, 0 then that is 0 or minus 1, like that. So v greater than 0, v equal to 0, and v less than 0. So I have this kind of mathematical model, and if you solve it, it is possible to show. Now you can see that time of convergence is not depending on the initial condition. So whatever your initial condition, any initial condition you can tell, either you can take 50,000 or 5, but your time of convergence is bounded by this particular time only. Okay, so time of convergence is practically not going to depend on the initial condition, and due to that reason, this type of convergence is called fixed time convergence. And most of whenever you are going to design some kind of parameter estimation problem, whenever you are going to solve some kind of estimation of means observer design problem, this kind of stability is equally useful. Another notion we have coined recently, that is called arbitrary time stability. It means that what we have observed, that it is possible to show that one can coin some kind of differential equation where here time of convergence is function of parameter, system parameter kd, kvm. It is possible to show that is independent of all system parameter, and that kind of stability is called arbitrary time stability. So if you see the classical literature, then in classical literature, most of time people are going just talking about stability, asymptotic stability, exponential stability. Later, if you see the recent development, since you all are PhD student, due to that reason I have covered this, that you have to also understand what is difference or intuitive idea of finite time stability, fixed time stability, or arbitrary time stability, and how basically we are characterizing stability here by solving the differential equation. So this is not geometrical way, by seeing the solution, and after that we are going to see the behavior of the differential equation. And so one can also establish the notion of stability by solving the differential equation. Obviously solving of nonlinear differential equation is not an easy task. So now let us come to the conclusion part. So if you know this kind of stability, so using the notion of this stability, you can also able to design the control action. So how, suppose now I have some kind of first order system, you can take UT and you have to design UT. So what now you can do, whatever things you have read till now, you can apply. You can replace U by minus xt or kxt. So you can see that system is asymptotically stable, because if you substitute here, so graphically also you can see here, this is MATLAB plot. So MATLAB plot means never they are going to become zero. They takes lot of time, t equal to infinity. Now what you can do, you can just change control by minus signum xt. It is possible to show that if you are going to start, initial condition is 2, within 2 seconds you can convert. If initial condition is 5, you are going to convert in 5 seconds. So somehow here time of convergence is function of the initial condition. After that, just you can modify control like this. This is complicated control. I am not telling how basically this control comes into picture, but it is possible to show that you can start anywhere. You are going to converge here. After that, recently we have coined this kind of controller, and it is possible to show that you can start anywhere. But if you fix TF equal to 1 second, so within 1 second you are going to converge. So that is called arbitrary time stabilization. So based on my knowledge, these are the notions or intuitive notion of stability. Okay, so first notion, what you can do, using help of potential like function or potential function, you can able to geometrically you are able to demonstrate by the analogy of ball analogy, you can tell. Second way, just using Newton's law, I am able to talk about stability. Third way, by solving the differential equation, and after that analyzing the differential equation, I can talk about the stability. So this is intuitive idea. In the next part of this course, obviously in not next lecture I am going to talk about the phase plane analysis, and after that I am going to talk about the notion of or epsilon delta notion of the stability or stability using the Lyapunov way. Okay, so till now if you have confusion, then please let me know. Anyone? Rajesh, are you here?
No, sir. Yes, yes, sir.
Any confusion?
No, sir.
Okay, so if you don't have confusion, then I am going to stop the today's lecture. Okay.